Welcome to This Explainer. You know, we interact with electricity every single day. I mean, you're literally using it right now. But when we actually stop to look at the source material and decode what is happening behind your walls and inside your devices, it is nothing short of mind-blowing. Today, we're going to explore what current actually is, how it behaves, and uncover a centuries-old scientific mistake that, believe it or not, we are all still living with today.
But hey, before we get into the heavy physics of it all, I want to hook you with a bit of a historical mystery. What if I told you almost everything you learned about the direction electricity travels is entirely backward? What if the symbols and diagrams we rely on every single day are based on a totally wild guess from hundreds of years ago? Keep that in the back of your mind as we go through this, because the answer completely shifts how we understand the invisible forces powering our modern world.
All right, Section 1, the basics of current. Let's get grounded here. At its core, electric current is really just the flow of electrons marching together in the exact same direction. If electrons are just randomly bouncing around, going whichever way they please, you've got zero current, nothing. But when they're forced to flow in unison, they follow a highly specific path called a circuit. Now, for those electrons to actually flow, this circuit must be completely closed. That means there has to be a continuous, absolutely unbroken connection all the way from the negative side of an energy source to the positive side. When that complete path is there, the electrons have their marching orders and they flow straight from negative to positive. And this brilliantly illustrates why the simple things in your house, like your light switches or your circuit breakers, actually work. Think about it. On one hand, we have an open circuit. This just means there's a physical break somewhere in that path. Because of that break, the electrons are totally trapped. They can't pass through, which means absolutely no current. But on the flip side, we have the closed circuit. The connection is complete, and the electrons are flowing freely. So when you flip a switch on your wall, you aren't creating electricity. You're literally just physically closing or breaking the circuit to either allow or stop that continuous flow.
Now, obviously, just having electrons run around in a circle wouldn't do us much good, right? We need them to actually do some work for us. So when the circuit is closed, those flowing electrons are forced to pass through electrical components placed along their path. As they squeeze through, they interact with the material that makes up those components, causing the material to react in a specific way. Take a classic filament lamp, for example. As the electrons force their way through it, the filament reacts by heating up and producing light, or simply harnessing their journey to get the results we want.
Which brings us to Section 2, a huge historical blunder. So way back in the 17th century, early scientists were desperately trying to figure out what caused electric current. They hadn't discovered the electron yet, so they kind of just guessed. They hypothesized that there was this electric fluid. They figured positively charged objects had an excess of this fluid, and negatively charged objects lacked it. Naturally, they concluded that this fluid must flow from high potential to low potential, from positive to negative. Makes sense, right? Well, fast forward to the 19th century, and science finally discovers the electron. And guess what? They realize that negatively charged objects are actually the ones with the excess electrons, and they flow from negative to positive. The exact opposite of that 17th century guess. But here's the crazy part. By the time they figured this out, it was way too late. All the textbooks were already written. All the electrical symbols were fundamentally designed based on that positive to negative direction.
Because it was just too much of a hassle to change everything, we ended up with the rather strange system we use today. We literally have two ways of looking at current. We've got conventional current, which flows from positive to negative. The word conventional basically just means it follows the old convention from before we knew any better. And then we have electron flow, which is the actual physical reality of electrons moving from negative to positive. So which one do you use? Well, both. If you're doing electrical calculations, conventional current is fantastic because you get to work mostly with positive numbers. But if you're doing actual hands-on electrical work, or you're trying to understand how components like diodes truly function on a physical level, you absolutely have to use electron flow. Whichever you use, the math works out the same, but man, what a fascinating quirk of scientific history.
Moving right along to Section 3, direct versus alternating current. Let's talk about how these electrons actually behave in motion, because there's a crucial difference here. On one side, we have direct current, or DC. In DC, the electrons flow in strictly one direction because the polarity never changes. Think of it like a strict one-way street. But on the other side, we have alternating current, or AC. In AC, the electrons are constantly changing the direction they flow. Why? Because the polarity keeps flipping. Remember, electrons are always trying to flow toward the positive polarity. So, if that positive polarity keeps flipping back and forth, the electrons are going to continuously reverse their direction just to chase it.
So how do we actually get that polarity to keep changing so we can create alternating current? It's pretty clever, actually.
The most common way is simply by manipulating a magnetic field. You basically take a magnetic field that's covering your conductor coils and you physically rotate it. As that magnetic field rotates across the conductor, the polarity continually shifts, which forces the electrons inside to constantly change their direction.
Let's tie this directly to the electricity running through your home right now. That rotating magnetic field we just talked about doesn't just spin whenever it feels like it. It operates at a highly specific frequency. Frequency is just the number of full cycles completed in a single second, with one cycle meaning the magnetic field has rotated all the way back to where it started. Most countries operate on either a 50 Hz or 60 Hz frequency. If your country uses 50 Hz, that means the magnetic field is rotating 50 times every single second, and those electrons are reversing direction incredibly fast just to keep up.
Finally, Section 4, measuring the electron flow.
When we talk about measuring current, what we're really doing is measuring the rate of flow. Think of it like measuring traffic on a busy highway. To do this, we use a neat little instrument called an ammeter. The setup is genius. To measure the current passing through a specific component, say a light bulb, you have to connect the ammeter in series with that component. This means you place the ammeter directly in the path, so every single electron that passes through the light bulb is forced to also pass through the ammeter. The ammeter acts exactly like a toll booth, literally counting the number of electrons passing through it every second, and it displays that measurement in a unit called amperes, or amps.
Prepare to have your mind blown a little bit here, because the sheer scale of this is just staggering. When that ammeter on your workbench displays a reading of just 1 single ampere, you might think, okay, 1, that's a tiny number. Actually, 1 amp translates to 6.28 quintillion electrons. That is, 6.28 with 18 zeros behind it. That absolutely incomprehensible number of electrons is rushing past that specific point in the circuit every single second just to give you 1 single amp of current. It really puts into perspective the microscopic size and the massive volume of these charges at work.
I really hope this explainer completely changes how you look at the electricity flowing through your own home and devices. It's not just magic happening behind the drywall. It's quintillions of tiny charges being aggressively forced along a closed path, sometimes reversing directions 60 times a second, all while adhering to a naming convention that was scientifically disproven centuries ago. So I'll leave you with this. Next time you flip a light switch, what are you going to picture? The conventional current neatly flowing from positive to negative like the old textbooks say, or the chaotic reality of quintillions of electrons rushing in the exact opposite direction? Thanks for hanging out with me for this explainer, and stay curious.